Hello learners, on behalf of Indira Gandhi National Open University, we welcome you for this video lecture session. I am Subhasis Maji, Professor in School of Engineering and Technology from Indira Gandhi National Open University. Today's topic is volumetric efficiency of reciprocating compressor. After listening to this video lecture, you will be able to understand the concept of work of compression. You will be able to know the volumetric efficiency of reciprocating compressor. You will be able to explain the clearance volume. You will also be able to solve the numerical related to volumetric efficiency of reciprocating compressor. Dear learners, let us begin our discussion. Work of compression by reciprocating compressor. A typical indicator cut obtained from a reciprocating compressor is shown in figure 1. The sequence of operation in the cylinder is first compression, starting at maximum cylinder volume point C, slightly below the inlet pressure P1. As the volume decreases, pressure rises until it reaches at point D. The discharge valve does not open until the pressure in the cylinder exceeds by enough to overcome the valve spring force. Next one is discharge. Between D and A, gas flows out at a pressure higher than by the amount of pressure lost through the valve at A. The point of minimum volume, the discharge valve is closed by its spring. Now, this is the diagram for the arrangement of single stage reciprocating compressor. On the left side, you will see the piston cylinder arrangement where the compression process is going on. Now the piston will move from top dead center to the bottom dead center while in the suction process, and from bottom dead center to top dead center the piston will move for the compression process. Now we have just discussed about the compression process which starts from the point C. As the piston moves in the upward direction, the volume will decrease and also the pressure will increase. At the point D, it will move to the end of the compression process. After that, the pressure has to be little bit high than the discharge pressure so that the gas will be entering into the receiving tank. Now at the point A, the piston position is at the clearance volume, and with that volume the high pressure, high temperature air will be there inside the piston. Now next is expansion. So when the expansion takes place from point A to point B, so during that period the pressure will decrease and the volume will increase. But till the point B, the inlet valve will not open, because at the point B the pressure of the air will be the atmospheric pressure. Now if it moves further in the downward directions, then definitely the volume will increase and the pressure will be below the atmospheric pressure and the inlet valve will open and the air will enter inside the cylinder, and the suction process will continue from the point B to the point C. At the end of the suction process, that is point C, again the compression will start as we have discussed. So let us see the other two processes for the reciprocating compression. So this is another diagram for the arrangement of single stage reciprocating compression. You see on the left side the reciprocating compressors diagram is there, and on the right side we call it the air receiver. The high pressure air will be stored in the receiver, and obviously when the high pressure air we will supply, then there is a discharge control valve. Now expansion from point A to B, as the volume increases, the gas remains in the clearance value expands and its pressure falls. The suction valve does not open until the pressure falls sufficiently below to overcome the spring force. Next one is intake, that is intake of air inside the cylinder. Between B to C, the gas flows into the cylinder at a pressure lower than the amount of pressure lost through the valve. The total area of the diagram represents the actual work of the compressor on the gas. The cross-hatched area of the diagram above and below represent work done solely because of pressure drop through the valves and port passages. This work is called the valve loss. The idealized basin to which an actual machine is compared has an indicator diagram like figure 3. We will see the figure 3 later on, in which there are no pressure loss effects and the process B to C and D to A are reversible polytropic processes, assuming no state change in the intake A to B and discharge C to D processes, and assuming equal of the exponent N in the compression from B to C and expansion processes D to A. The ideal work of compression can be found by taking the integral of PdV around the diagram. The work done on the air during the cycle is equal to the enclosed area A, B, C, D. Now, this is the indicator diagram. You see that from B to C, this is polytropic compression process, and C to D is the constant pressure process, and again D to A is polytropic expansion process, and A to B is constant pressure process. Now we will see how to calculate the net work done for the entire compression process. Now that is nothing but the area under the curve A, B, C, D. It is the area of A, B, C, D. Now the area of A, B, C, D, we can calculate the area of C, D, HF plus area of H, E, B, C minus the area of D, A, E, H and minus B, E, G, A. Now let us see how we can calculate the work done. But dear learners, we have already discussed how to calculate the work done for the polytropic process, how we can calculate that we know for the constant pressure process. Now we will see for this case how we can calculate the net work done for the compression process for the reciprocating compression. Work done on the air during the cycle is equal to enclosed area ABCD, that is equal to area DCFH plus area CBEF minus area HGAD minus area GEBA. Now the net work done we can calculate, because we know how to calculate the work done for the constant pressure process. We know how to calculate the work done for the polytropic process. Now here W is equal to P2 multiplied by Vc minus Bd plus P2 Vc minus P1 Vb whole divided by n minus 1, because it is a polytropic process, minus P2 Vd minus P1 Va divided by n minus 1, it is also a polytropic process, minus P1 multiplied by Vv minus Va. So finally we will get the work done is equal to n divided by n minus 1 whole multiplied by P2 Vc minus P1 Vb minus P2 Vd minus P1 Va. We know that P2 Vc is equal to MC RT2, P1 Vb is equal to MB RT1, and MC minus MB is equal to mass of air taken at the time of compression. Also P2 Vd is equal to MD RT2 and P1 Va is equal to Ma RT1, because this is the equations for ideal gas. PV is equal to MRT, and Ma minus Md is equal to mass of air in the clearance volume after delivery. Now if you put these values and if you rearrange the equation, finally we will get the work done per cycle is equal to n divided by n minus 1 Mb minus Md multiplied by RT1 multiplied by P2 by P1 to the power n minus 1 by n minus 1. But Mb minus Md is equal to difference between the mass of air present at the end of suction and that present at the end of delivery. Now we will talk about the volumetric efficiency of reciprocating compression. The flow capacity of positive displacement compressor is expressed in terms of volumetric efficiency, that is equal to eta volumetric efficiency is equal to mf small v1 divided by pd. Here mf is the mass of fluid flow per machine cycle and pd is the piston displacement volume per machine cycle. The true volumetric efficiency can be determined only by measuring the flow through the machine. An approximate or apparent volumetric efficiency may be obtained from the indicated diagram shown in figure 4 and 5. Here the volume V, that is equal to V2 minus V1, is the volume between the point where the cylinder pressure reaches P1 during the expansion process and the point where it reaches P1 during the start of the compression process. This is the indicated diagram for the compression process. So 2 to 3 is the polytropic compression and 3 to 4 is the constant pressure process for delivering of the air in the receiving tank, and 4 to 1 again is the polytropic expansion process, and 1 to 2 is the constant pressure suction process. Now Vs is given as the sweep volume, that means piston is moving from the top end center to the bottom dead center. So here Vs is known as the sweep volume and Vc is the clearance volume. If the gas remained at constant temperature during the intake process, the volume V would be the actual volume taken at state 1, then the ratio V by PD would be the volumetric efficiency. In an actual compressor, because of heat transfer from the cylinder walls, the gas is at higher temperature after entering the cylinder than at state 1. Consequently, the volume V is greater than the volume taken in from the supply line, and the ratio V by PD is larger than the true volumetric efficiency, hence the name apparent volumetric efficiency. The volumetric efficiency, the eta volume, is a measure of the effectiveness of the machine with regard to gas handling. So, eta volumetric efficiency is equal to volume of gas actually compressed and delivered as measured at inlet pressure and temperature divided by piston displacement. This can also be said, that is, eta volume is equal to mass of gas actually compressed and delivered divided by mass of gas occupying the piston displacement at inlet pressure and temperature. Now, eta volume is equal to m small v1 divided by piston displacement. Small v1 is the specific volume at state 1, is equal to m v1 is divided by vs, because piston displacement is equal to vs. Here m dot is equal to mass flow rate of the gas, and small v1 is the specific volume of the gas at the inlet. So, eta volume is equal to v2 minus v1 by vs is equal to vc plus v2 minus v1 divided by vs. So, eta volume is equal to v2 minus v1 by vs and is equal to vc plus vs minus v1 whole divided by vs equal to 1 plus vc by vs minus v1 by vs. Now, CL, that is equal to vc by vs, and we can also write the equations, that is P1 V1 to the power n is equal to P2 V4 to the power n. So here V1 we can write equal to V4 multiplied by P2 by P1 to the power 1 by n, but V4 is equal to the clearance volume Vc. So V1 is equal to Vc multiplied by P2 by P1 whole to the power 1 by n. So after rearranging these expressions, we can write that the volumetric efficiency is equal to 1 plus Cl minus Cl multiplied by P2 by P1 to the power 1 by n. Finally, we will get the expression for eta volume is equal to 1 minus Cl multiplied by P2 by P1 to the power 1 by n minus 1. Now you have got the expressions for eta volume, but you see that when the P2 by P1 is equal to 1, in that case the Cl will be equal to 0. Now from this expression we can also get the maximum value of Cl. Now let us very quickly perform some numerical. Now this is the exercise 1. A reciprocating air compressor operates between 100 kilopascal and 500 kilopascal with a polytropic exponent of 1.3. How much clearance would have to be provided in the ideal case to make the volumetric efficiency 50% or to make it 0? My dear students, please see what are the data given for this particular problem. So here the final pressure is 500 kilopascal. The initial pressure is also given as 100 kilopascal. So P2 by P1, this ratio is given as 5. The value of n is given as 1 0.3. Now we have to calculate how much clearance would have to be provided in the ideal case to make the volumetric efficiency 50%, that is 0.50. Second part is to make it 0. Now let us see how we can proceed for this numerical. Now volumetric efficiency is given as eta volume is equal to 1 minus CL P2 by P1 whole to the power 1 by N minus 1. Now for eta volume equal to 50%, that is equal to 0.5 is equal to 1 minus CL within bracket the pressure ratio P2 by P1, obviously it will be equal to 5 whole to the power 1 upon 1.3 minus 1, because the value of N is given as 1.3. After doing the calculation, you will get the value of CL, that is equal to 0.204. So this is the first part of the numericals for the calculations of CL. The second part of this problem is what will be the value of CL when eta volume is equal to 0. Now in this case, start with the first equation. Eta volume is equal to 1 minus CL within bracket P2 by P1 to the power 1 upon N minus 1 is equal to 0. Now here again P2 by P1 is given as 5. The value of N is given as 1.3, but only thing you have to put the eta volume is equal to 0. If you do the calculations, you will find the value of CL you are getting as 0.408. Now let us proceed for the second numerical. It is given that a two-stage compressor is used to compress 10 meter cube per minute of air from 100 kilopascal to 1400 kilopascal. What will be the pressure in the intercooler for the special case of minimum work of compression? If N is given as 1.3, find the percentage saving in work by compressing in two-stage compared to single-stage compression. Now you see, this is the diagram for performing the compression operations in the two-stage. What is happening over here, that in this case that compression work, it is from 1 to X and X to Y, it is the cooling of the gas, so that after first stage compression the temperature of the compressed gas will come down to the initial temperature T1. After that the second stage compression will start from the point 1 and again it will be up to the point 3 for the polytropic compression process. Now let us see how much work we can get for the single stage and how much work we have to perform for the double stage compression process, and after that we have to calculate the percentage of work saving. The data given for this problem is flow rate is given as 10 meter cube per minute, initial pressure is given, P1 is 100 kilopascal, the final pressure is also given, that is 1400 kilopascal. But for perfect intercooling, the pressure ratio has to be same. Px by P1 is equal to P2 by Px, and therefore Px is equal to under root P1 multiplied by P2. If you know P1, P2, then Px, the intermediate pressure, you can calculate, that comes out to be 3.74 to the power 10 to the power 5 Pascal. Now once you know the Px, then for a single stage you can calculate the work done, and the double stage also you can calculate the work done for this particular problem. So minimum work total per minute is equal to W total is equal to 2 multiplied by N minus 1 P1 V1 multiplied by Px by P1 to the power N minus 1 by N minus 1. So you know very well how to calculate this because all the data are given, that is P1 is given, small v1, that is a specific volume, that is also given, and Px is also calculated, that is for this problem. And just put the values in these expressions and calculate W total, and for this two-stage compression the W total will be 3083.75 kJ per minute. Now for a single stage, that is from P1 to P2, from 100 kilopascal to 1400 kilopascal, how to calculate the work done? We will proceed in the same way, that is W total is equal to n divided by n minus 1 P1 V1 multiplied by P2 by P1 whole to the power n minus 1 by n minus 1. But in this case, dear learners, how to solve? Because see what are the values given for this particular problem. The value of n is given as 1.3, P1 is 100 kilopascal, and small v1 is given, and P2 by P1, that is 14, all the values are given, so there is no problem for calculating W total. So W total for this particular problem is equal to 3634 kilojoule per minute. So this is the process for single stage compression process. You have calculated W total, that comes out to be 3634 kilojoule per minute. So shaving in work is 3634 minus 3083.75, that comes out to be 550.25 kilojoule per minute. Now if you want to calculate the percentage saving in work, therefore saving in work is equal to 550.25 divided by 3634, that comes out to be 0.1514 or 15.14%. So dear learners, here we conclude our today's discussion on volumetric efficiency of reciprocating compression. We have discussed about the volumetric efficiency in detail. We have also discussed about some numerical. Now let us summarize our discussions very quickly. We have discussed the concept of work compression. We have discussed the volumetric efficiency of reciprocating compression. We have discussed the clearance volume. We have discussed the reciprocating compressor for two-stage compressions. Lastly, we have solved some interesting numericals related to volumetric efficiency of reciprocating compressors. Thank you very much.